The only other concept that is in section 5.2 is the concept of complement. The complement of an event. Now, I'm going to give you this formal definition, but it really isn't maybe as complicated as this definition might make it seem. Let S denote the sample space of a probability experiment, and let E denote an event. The complement of event E, which our textbook is going to denote by E with a superscripted C, that C's for complement, so this is E's complement, is all outcomes in the sample space S that are not outcomes in the event E. So in other words, the complement of event E occurring means event E doesn't occur. So it could be anything except event E. So I'm going to use my card example again. If we're looking at the event draw out a king, the complement of drawing a king is not drawing a king, meaning drawing out any of the other cards except the kings. So if this is the sample space of cards, right? If event E is drawing a king, then E's complement is all of the other cards that aren't kings. That's the idea. So I also want to address this notation, E with a superscripted C. That is not a particularly common notation that's used. A more common notation is E with, well, we call it a prime, but it kind of looks like an apostrophe up here. So this is E prime. That is a notation that's used frequently for the complement of E. Another symbol that's used is a negation symbol from logic. And so if I say that symbol, E, that also can mean E's complement. Basically, this means the negation of E, so not E. Now, this symbolism is used often in logic, but it does spill over and is used sometimes here with probability as well. So again, if you were to do a Google search or something, you would more likely see one of these two notations instead of this notation. Sometimes even just a negative sign is used. So you might say the negative of E, which basically means not E. So again, these notations are more commonly used. Complement rule. Now, if you think about what I just said here, if event E is drawing out a king, then the probability of drawing out a king would be 4 out of 52. The probability of E would be 4 out of 52. The probability of E's complement would be the other 48 out of 52. So E's complement would be 48 out of 52, okay? So to make a long story short, if I add the probability of an event plus the probability of the event's complement, it has to add up to 1. And so that's what this is saying. This is called the complement rule. If E represents any event and E complement there represents the complement of event E, then the probability of E's complement equals 1 minus the probability of E. So if I want to find the probability of the complement of an event, I can take 1 minus the probability of the event, and that will give me the result. Now, it's not included here, but in the same way, I could say that the probability of event E equals 1 minus the probability of E's complement. So this is equivalent. So oftentimes, the easiest way to figure out the probability of an event is by figuring out the probability of the complement, and then 1 minus that will give us the probability of the event. What I really kind of like to think of in general, though, is that the probability of the event plus the probability of the event's complement always has to add to 1. So it's the same rule. I could write it any one of these 3 ways, whichever way is most convenient for the situation that I'm dealing with. So, example, according to the US Census Bureau, the probability that a randomly selected worker primarily drives a car to work is 0.764. We want to find what is the probability that a randomly selected worker does not drive a car to work? So the probability that the person drives to work, the probability that they drive to work, we're given is 0.764. So the probability that they do not drive to work is going to equal 1 minus the probability that they drive to work. So that's going to be 1 minus the 0.764, which would be 0.236. So if the probability that a randomly selected worker drives to work is 0.764, then the probability that a randomly selected worker doesn't drive to work is 0.236. Now, what does it mean to not drive to work? Well, that means somehow you get to work some other way, right? So you might take a bus to work, you might take a train to work, you might walk to work, you might ride a bike to work, but you don't drive.